What we saw in the last video was that if we have some sort of electrical source and we connect it via wires to an electrical load, in electromagnetic analysis we need to analyze these wires as a transmission line. And from a circuit perspective, we use a resistor, an inductor, a capacitor, and a conductance to model the transmission line behavior or parameters or behavior. And remember, we called these R prime, L prime, C prime, and G prime, and collectively those are called the transmission line parameters. And that makes sense if you're thinking of electromagnetic waves in terms of electricity, which we will mostly do in this class. However, there's a more general analysis that we can apply to T-lines that is used by physicists, RF and microwave engineers, and electrical engineers just dealing it, with normal RF analysis. And that's called the Waveguide Model, and it's kind of a logical extension of the distributed parameters, and it's a usage that we apply to examine how an EM wave actually travels in a conductor. And what we're going to call this is the Waveguide Model. So what happens is we've got a source, and that source sends some sort of signal, electromagnetic signal out, and we typically think of that as a voltage generator, a signal generator, but it's any sort of radiation, right? It could be light, it could be X-rays or anything like that. And if we think of it in terms of a circuit, what happens is there's a voltage that is established between this conductor and this conductor, V, and that voltage is going to travel sinusoidally down the transmission line going towards the load. So this wave is kind of moving from the left to the right. And that's a phasor voltage. We say that it's got the fixed phasor, V bar plus, and the value of the wave is going to be a function of distance, so we've also got that distance varying voltage there. And because of the RLC network that represents this transmission line, there's also an associated current wave that's going to be flowing sinusoidally from the source to the load, and that is a current I is equal to I bar plus e to the minus j beta x. So it's a phasor current, and then there's this distance dependent property. In this model, the voltage wave corresponds to the E field, the electric field, in a less specific model dealing just with E and M, and the I corresponds to the B field of the wave. So if you're confused between, well, sometimes you're talking about electric fields and magnetic fields, and sometimes you're talking about voltages and currents. In a conductor, the E field establishes voltages, and in a conductor, the B field establishes currents. So these are kind of analogous there. So this source is going to establish a voltage and current wave that propagate along the line. It's guided by the transmission line from the source to the load. The transmission line is acting as a transmission medium, it's guiding it, and the wave will travel at the propagation velocity of an electromagnetic wave in that material. And so it's traveling at a propagation velocity, which is given by the material properties 1 over the square root of epsilon, the electric permittivity, times mu, the magnetic permeability of the material. As the signal travels along the transmission line, this voltage waveform is going to define both the magnitude and the angle of the voltage at any given point. So the magnitude and the angle of the voltage are going to change along position of the transmission line. And a similar thing can be said about the current. The magnitude and the angle of the current are going to change as a function of transmission line, distance along the transmission line. At any point, if we were to pick a fixed point, just any random fixed point along the transmission line, the ratio of the voltage wave V bar plus e to the minus j beta x to the current wave I bar plus e to the minus j beta x, which you can see simplifies just down to V bar plus over I bar plus. The ratio of the voltage to current is called the characteristic impedance of the transmission line. We saw how to calculate characteristic impedance in a previous video, but now I'm really telling you what is characteristic impedance. Characteristic impedance is if I apply a voltage to a transmission line, how much current flows, and the ratio of voltage applied to current that is established is the characteristic impedance. So it looks a lot like Ohm's law right there. We can calculate the characteristic impedance for a transmission line. For a lossy transmission line, we use that formula R prime plus J omega L prime, and we have G prime plus J omega C prime. And remember, this is for lossy. In a lossless transmission line, R is 0 and G is 0, so the J omegas here cancel out, and we're just left with Z0 equals the square root of L prime over C prime for a lossless T line. So those are our two different calculations for the characteristic impedance. And really what this number tells us is the ratio of voltage to current in a transmission line, whether it's lossy or lossless. Right there. What is going to happen when this voltage waveform reaches the load? This point right here where the transmission line connects to the load, we call that an impedance boundary, and we spoke briefly about how that's going to cause a reflection. Well, that reflection means there's another voltage waveform and another current waveform flowing in that opposite direction. And the reflected waves, they have a different notation. The reflected voltage wave is going to be V bar minus, indicating that it's traveling in the reverse direction, and it's going to be traveling from right to left, so it's e to the j beta x. And there's a reflected current wave, which is I bar minus e to the j beta x. And the characteristic impedance Z0 also tells us the relationship between the reflected voltage wave and the reflected current waveform, with one important difference. We actually have to put a minus sign on there. And I'll explain mathematically where that minus sign comes from next lecture. But for right now, just know that the characteristic impedance is either the ratio of the forward voltage wave traveling from left to right to the forward current wave traveling from left to right, or it's the opposite of the reverse voltage wave when the reflection occurs, traveling from right to left, to the reverse current wave traveling from right to left. So don't forget that minus sign when you're talking about those two reflected waves. Interestingly, some students make the mistake, and it makes sense. They think that Z0 is the total sum of voltage and current on a transmission line, meaning the sum of the forward and the reflected waves. So they think that it should also therefore be V bar plus V bar minus over I bar plus I bar minus. And it turns out that this is not the case. This is not true. We'll explain why in a later lecture, but just know that that is a mistake that's often made. That statement is correct, and that statement is correct for what the characteristic impedance can tell us about a circuit. We can also use these distributed parameters R prime, L prime, G prime, and C prime to determine a couple other properties of the transmission line. And this property we're going to call gamma, lowercase gamma, and it's called the complex propagation constant. It doesn't have any units, and it is equal to the square root of R prime plus J omega L prime times G prime plus J omega C prime. So you can see it's very similar in form to the lossy form of the complex, or of the characteristic impedance of the transmission line. This is going to result in a number that has a real portion of it and an imaginary portion of it. We call the real portion alpha, and we call the imaginary portion beta. That's the result of this. And we've already talked about these two numbers before. This is the attenuation constant, and it's measured in meters per meter. And this is the wave number, and it's measured in radians per meter. And if you've forgotten where those come from, just remember that V of x comma t is equal to V peak cosine of omega t minus beta x plus theta. And that's for a lossless line. And for a lossy line, we've got Vp e to the minus alpha x cosine of omega t minus beta x plus phi. And that's the attenuation constant, and those are the wave number for either a lossless or lossy transmission line. So we can extract some really useful information about the voltage waveform from the distributed parameters R prime, L prime, G prime, and C prime.